Okay, in this presentation we are going to look at the beta type 1 distribution. There's two beta distributions, the type 1 and the type 2. In this instance we'll be looking at the type 1. A continuous random variable x is said to have a beta type 1 distribution where parameters alpha and lambda, just as a sort of quick remark there, usually we would specify it as alpha and beta, but for some reason my setup here does not like beta. Of all the Greek letters, it does not like beta. So just for today, I'm going with lambda, but usually we would write that as beta, or quite common. It's quite common to mix up notation anyway, so don't get too fixated that certain distributions should have certain types of notation. Anyway, this is the PDF, the probability density function here. Okay. F of x equals 1 over beta of lambda, alpha lambda. Okay, so that's the beta function, or the inverse of the beta function. And this expression here, x to the power of alpha minus 1 times 1 minus x to the power of lambda minus 1 for 0 less than or equal to x less than or equal to 1. Okay. Now, so there's a couple of things actually to remark upon here, and couple of the key things are really down here in this part here. Okay, the beta function. So essentially, this is going to do a lot of the hard work. Beta of alpha lambda is equal to the gamma function of alpha times the gamma function of lambda divided by the gamma function of alpha plus lambda. Okay, now this is also equal to this expression here. Usually this is the type of thing that would turn up at the back of an exam paper. The integral from 0 to 1 of x times x to the power of alpha minus 1 times 1 minus x to the power of alpha minus, or lambda minus 1. That is the beta function. Okay, and you can sort of see pretty quickly that this actually corresponds very closely to what we have above. Okay, this is the gamma function here. This is just to sort of say this is the gamma function denoted in terms of alpha. It could be beta or any sort of integer really. Okay, now and in notation we write this variable x as beta. X is distributed as beta 1 alpha lambda. Now again, you might sort of see it as this in other books. Again, part of what's going on there is just my setup is not liking betas. But anyway, we'll push on. It's handy to know if you're dealing with alpha and gamma distributions, just to note some of the mathematics associated with alpha and gamma. Now, I just notice here that we also have a problem here with regards to factorials. Okay. So that is, I think I have most of them there. So just to sort of see that the setup is also not liking factorials. I didn't notice that. Anyway, the gamma function of n is n minus 1 factorial. So that is to say the gamma function of 3 is 2 factorial, which is equal to 2, and likewise the gamma function of 4 is 3 factorial, which is 6. Okay, and it's handy to know these little results. Okay, just sort of have them ready in your head. The gamma function is straightforward enough. You should be familiar with the factorial function. Okay, so what we have to show here is that the mean of the beta type 1 distribution is given as follows. The expected value of x equals lambda divided by, equals alpha divided by alpha plus lambda. Okay, so straightforward enough, really. This actually looks really complicated when you, in the first instance, but essentially we're going to take the usual sort of format. We have x times the probability density function. Okay, now this is essentially a constant in terms of x. Okay, so we can bring it out here. Okay, and what we actually have here is something denominated in terms of the beta function. Okay, So just remember this x here comes into it, and that term there, we can combine them into x to the power of alpha. Now I just sort of left it alone there, x to the power of alpha plus 1 minus 1. And that makes clear that this is a function, this integral here is actually can be written as a beta function, okay, down here, okay. So it's beta of lambda, alpha plus 1 lambda, okay. So that's the sort of key thing there. So just going back to that definition, I'll just go back up to it. This one here. Perfect. That's all we need. That should be at the back of your exam paper. Okay. Now, this actually breaks down very quickly. Okay. So what we end up with here is the beta function of alpha plus 1 lambda divided by the beta function of alpha lambda. Okay. So we can use our expressions here, express them in terms of the gamma functions. Okay, so the numerator is there, and the denominator will just invert it over here and multiply them out. So essentially what we can do now is just cross multiply them out. The gamma function of lambda, gone. Okay, and that's it so far. Yeah, so the gamma function of alpha plus lambda plus 1 can be written as alpha plus lambda times the gamma function of alpha plus lambda. So that crosses out, okay. And yeah, they just sort of cross out with each other basically. So the gamma function of alpha plus 1 is equal to, this expression here is equal to that, can be re-expressed as that, alpha times the gamma function of alpha. So we have an expression there in terms of the gamma function of alpha. Essentially all sort of cancels out, okay. So really what's going on in this section here is just a load of cancellations, okay, and we end up with this expression here, okay. Now, just actually watch out that, off the top of my head, but usually alpha and beta have to be greater than 0 or greater than 1. Okay, so just remember to stick that in. Yeah. I didn't really express it in this case, but just, you know, watch out for those constraints on the parameters alpha and lambda. All right. So we'll look at the variance of the beta type 1. Okay. And it should be fairly similar enough. The variance of the beta type 1 distribution is as follows. Variance of x equals alpha times lambda divided by alpha plus lambda squared times alpha plus lambda plus 1. Okay. Now, this actually is the very same sort of approach. It's just a little bit long-winded. Remember that key identity there. The variance of x is equal to the expected value of x squared minus the expected value of x to be squared. That comes up so often in these sort of questions, so make sure you have it off by heart. Okay. Now we're going to take the same sort of approach as we did the last time. We calculate the expected value of x squared. Okay. So that is the integral of x squared times the probability density function, dx. Okay. Same sort of approach. We're going to factorize, take this out and have it as a constant. And what we end up with here is this expression here. X to the power of alpha plus 2 minus 1 times 1 minus x to the power of alpha minus 1. Okay, and we get the integral of that, dx. And that can be expressed as the beta function of alpha plus 2 lambda. Okay. So what we have here is this, and essentially it's the same sort of calculations again to simplify it, okay? And you know, using the beta function of alpha and lambda, and that is equal to the gamma function of alpha times the gamma function of lambda divided by the gamma function of alpha plus lambda, and also this gamma function of alpha can be expressed as alpha minus 1 times the gamma function of alpha minus 1. Sort of used those already. I probably should have mentioned them before. But anyway, we'll persevere. So the numerator is the gamma function of alpha plus 2 times the gamma function of alpha. Okay, so we can start cancelling stuff out. The gamma function so that's the gamma divided by the gamma function of alpha plus lambda plus 2. Okay, and that can be rewritten as alpha plus lambda plus 1 times alpha plus lambda times the gamma function of alpha plus lambda. Okay, and those two cancel out. Okay, lots of cancellations. Okay, so that means that the expected value of x squared is alpha times alpha plus 1 divided by alpha plus lambda times alpha plus lambda plus 1. Okay, now this part of the calculation is not very pretty. Okay, it just takes, it's actually fairly straightforward, really. You know, you're not really dealing with any hard integrals. You're just dealing with gamma functions for most of it. But anyway, we'll persevere. So the expected value of x squared we have there, and the expected value of x to be squared is alpha divided by lambda plus alpha divided by alpha plus lambda. Those get tongue-tied, to be squared. Okay. What I'm going to do is actually factorize it out a little bit. So I have this expression here and this expression there. Okay, and just factorize it out. So I have alpha times alpha divided by alpha plus lambda by this. Okay, and what I can do there is cross multiply and cancel out. Now it's a straightforward enough algebraic operation, okay, but just take your time with it. What happens is that they cancel out. You work through it. Alpha squared cancels out. Alpha times lambda cancels out with that minus alpha times lambda. That alpha cancels out with that alpha, so we are just left with lambda. Okay, and that is the answer there. Alpha times lambda divided by alpha plus lambda squared times alpha plus lambda plus 1. All right. Okay, so what's the key thing there actually was, that was not so bad really compared to what you could get. But we just noticed that the beta functions and the gamma functions did a lot of the heavy lifting there. Okay, so just being really good with those helped work things out very quickly. So if you get a beta distribution question coming up in your exam paper, derive the mean and the variance, don't hesitate, go for it. It's actually straightforward. Okay, we'll leave it there.